Hey folks, today I'm going to discuss about spectral theorem and its significance. I've been reading this book, Mathematical Foundation for Machine Learning, and there's a topic called spectral theorem. I did a little research on YouTube videos and things like that. There's so much content, but it really didn't bring it all together. So I thought I'll create one real quick video on spectral theorem, right? So to begin with, what is spectral theorem? Why do we need spectral theorem and things like that, right? So the mathematical theorem states that it is nothing but a real symmetric matrix that can be diagonalized by an orthogonal matrix, right? That's very technical. What I'll do is I'll break it down into three chunks, which are bold, which is symmetric, diagonalized, and orthogonal. What do we mean by that, right? But before I really explain what is spectral theorem, I wanted to understand what are the real world applications that we can use spectral theorem. So what's in it for us, kind of thing, right? So I did a little bit of research, and one good example that I can think of, there's a lot of examples, right? You can see from the slide, but one example really I could connect is the computer graphics. The image processing, right? So in the resource extensive world, the compute power that we want to use it, lesser, cheaper, and whatnot. So basically, what spectral theorem can do for us in terms of image processing is, if you diagonalize it, right? A high resolution image, by doing diagonalization, you kind of decompose the image matrix, and let's just keep the middle diagonal matrix, right? Which can have the values. By only retaining that, what you're doing is you're basically compressing the image without losing the quality. And basically, instead of say a huge n cross n matrix, you diagonalize it and you only send the diagonal elements of the matrix to store or to transmit, right? Basically, you're eliminating the rest of the noise. So it saves your compute power, it saves your cost. So that's basically one good example, but there are so many other examples. Now let's talk about what is spectral theorem, right? Like I said, the three important terms are symmetric, orthogonal, and diagonalized. Obviously, it should be a real square matrix, n cross n matrix, with same number of rows and the same number of columns. It needs to be symmetric. So what is a symmetric matrix? A symmetric matrix is nothing but it's a square matrix, obviously, and it should basically be the same as its transpose, right? So A is equal to A transpose. Let's take an example of a matrix A, 2, 1, 3, 1, 4, 5, 3, 5, 6. Now, if you do a transpose of it, basically you move the columns to the rows and vice versa, right? So basically it should be the same. So A transpose should be equal to A. That is symmetric matrix. So this theorem kind of proves that once you diagonalize it by an orthogonal matrix, the matrix will remain symmetric. So then the next question is, what is a diagonal matrix? Diagonal matrix is nothing but, as you could see from the image in the middle, the diagonal element will have values. The rest of all will become zero, right? Zero on all of non-diagonal elements. So that's what diagonal matrix means. Now, what is spectral theorem? Basically, spectral theorem intends to do diagonalization, and it does it in 5 steps, right? Step number 1 is finding the eigenvalues. I'll talk about what is eigenvalues. Finding eigenvectors. Again, I'll talk about what is eigenvectors, and then using the eigenvalues and eigenvectors, we form a matrix P. Then we form a diagonal matrix D. Again, we'll talk about how it is, and then we need to verify the diagonalization. So basically, diagonalization is nothing but the matrix A, right? We'll take a 2 cross 2 matrix example here. The matrix A should be equal to PDP inverse 1, which holds true, right? If we can prove that, then it means that the spectral theorem is working, the diagonalization is working, right? So that's what it is. Now, I've written a short code in Python to kind of showcase the eigenvalues, eigenvector calculation using Python. It's pretty simple, using NumPy, and then a 2 cross 2 spectral theorem is here. As you can see, the original matrix that I've used is 5 minus 2 minus 2, 8. It does the calculation of eigenvalues, which we'll do manually as well. And then the eigenvectors, likewise, do the diagonal matrix, which is nothing but putting your eigenvalues 4 and 9 diagonally. And then we reconstruct the matrix with the formula that we mentioned about PDP transpose, and we get that value, and then we verify it. It proves the orthonormality, and it proves the spectral theorem, right? So let's go to step 1, which is finding the eigenvalues. So the matrix that I've taken, a 2 cross 2, is 5 minus 2 minus 2, 8. The eigenvalue, the formulation is matrix minus lambda I, right? So basically you have a identity matrix and you have the you kind of multiply that and then you have the A matrix, which is 5 minus 2 minus 2 8, which becomes 5 minus lambda minus 2 minus 2 8 minus lambda, right? And then you need to calculate the determinant. You can do it by yourself, or you can also use the FX991 CW Casio calculator. You'll get the determinant. So basically, once you find the determinant, which is lambda squared minus 13 lambda plus 36, that's a characteristic polynomial, right? And then you calculate the eigenvalues. So for lambda squared minus 13 lambda plus 36, you can see mathematically lambda minus 4, lambda minus 9. It is nothing but it is lambda squared minus 13 lambda plus 36. If you just multiply lambda minus 4 and lambda minus 9, you will get this characteristic polynomial, right? And then basically you get the two lambda values, which is lambda is equal to 4 and lambda is equal to 9, right? So we are done with eigenvalues. Now we need to do eigenvectors, which is nothing but we substitute the values of lambda is equal to 4 and lambda is equal to 9 in this formula of eigenvectors. A minus lambda I, which we read before. So basically we are substituting that values, which becomes A minus 4 lambda is equal to 0. So it becomes 1 minus 2 minus 2 4. We are putting x and y here. And then basically the first values, right? 1 minus 2x, you take it as x minus 2y is equal to 0. So here we are doing a substitution of y is equal to 1. You can substitute a value to calculate the value of x, right? And likewise, when we do lambda 2 is equal to 9, we'll substitute x is equal to 1 as an assumption, and then we will find the value of y. So basically what will happen is the eigenvectors here will become 2 comma 1, and here the eigenvector will become 1 comma minus 2, right? Once we are done with this, we'll have to put this in the columns of P. That's a step 3, right? So again, we'll use for lambda 1 4 and for lambda 2 value of 9, we will substitute that in your column P, and we'll have to normalize this. So the normalization of root 5 is nothing but we calculated using the magnitude of this 2 cross 2 matrix, and it comes down to root 5. So 2 by root 5, basically what we did last in the previous one, right? We know the value of y, we know the value of x, so we substitute that for 2 by root 5 and 1 by root 5. We get the value, and then we get the normalized eigenvectors as columns, which is 0.8944, whatever the value you see at the bottom of the screen, right? Once you're done with this, so we'll have to construct the diagonal matrix, which is step 4. We know the eigenvalues of lambda 1 and lambda 2. We substitute that in a diagonal fashion. Diagonal matrix, as we all know, the diagonal should be the numbers, and then anything other than that should all be zeros. So we do that. And then the step 5 is nothing but we'll have to reconstruct it in the formula, which is the matrix multiplied by PDP transpose, right? So we put all those values here, as you could evidently see, and then we do metric multiply step by step, and then you get 5 minus 2 minus 2 8, and if you remember, that's exactly what the matrix A we had, right? So basically that's how spectral theorem proves that the matrix A that you had, you diagonalize it, you will be able to get the same reconstructed matrix in the original form of matrix A, right? So that's it for now. The next video I will create on SVD and EVD. Thank you. And any questions, please put it in the comments.